So from this video, I have started a new series called as unsupervised learning. So the famous algorithm in unsupervised learning is K-means. So what is unsupervised learning? First of all, let's focus. Let me, you know, bring some light to that idea. So unsupervised learning doesn't have a target label like in supervised learning, and the focus is to create the clusters. What is a cluster? Cluster is a group of similar data points, and the formed cluster should be as different as possible. So K-means is an algorithm that creates the similar clusters. So why we need such an algorithm? Why not a simple method like binning is enough? We can use pd.cut to create bins, and why not that is enough. So let us explore this idea first, so we can so I can understand the why k-means is important. So there are some constraints in the binning method, like equal width bins is a constraint. Let's say let's say I have a group feature called group, and I create a age group from 0 to 20, 20 to 40. But the 20 of a person of 20 and 21 age are quite similar only. They are not different persons. They are not they should not belong to the different clusters altogether, right? Just by hard coding the bins boundary, or bins the upper bound of the, just by fixing the boundary, I am creating a constraint to my data which doesn't represent my actual data, but it's imposing a limitation. So that's why binning is not useful here. Let's say there is also, it also breaks assumptions of, it also makes an assumption of that my data is normally distributed. Like let's say if a monthly spend, for a monthly spend feature, the bins might look like 0 to 500, 500,000, and 1000 to 1500, and so on. But for this bin 1000 to 1500, my there are no number of there are no data point belongs to this cluster. So this bin is useless. So it can happen with multiple variables, where some we have some empty bins, or some bins are not completely useful. So we cannot hard code the boundaries. We need some dynamic boundaries that can adopt to my current data set, so that the form cluster are clearly separable. So the question k-means ask is, where should be my boundaries so that similar points stay together? K-means learns boundary from the data that separates a data point into k groups. So k-means is not making assumptions about the data and then creating the boundaries. Instead, it's learning the boundaries from the data that can separate the data points into k groups. So this makes the k-means so famous and robust. So k-means relies on WCSS, which is within cluster sum of squares. So within cluster sum of squares can be visualized as, for these three data points we have a centroid, and the distance of each data point from its centroid, when squared and added for all the clusters that we that I have that the k-means have created, is called the WCSS. So it's a sum of all the clusters and all the data points from the mean, from its centroid. So k is the number of clusters, C is the number of cluster, k is the number of clusters, Ci is the cluster of I, and centroid of the cluster U, and xj is the data point. And we compute the distance between two data points, the centroid and the data point, using the Euclidean distance. So Euclidean distance, we know that is given by this formula. I'm aware that is given by this formula. K means learns the optimal position of centroid by minimizing WCSS. There are some terminologies in K-means, which is a cluster. What is a cluster? What is a centroid? So cluster is nothing but a collection of similar data points, and centroid is average position of all the points inside the cluster. Let's say we have 2 points, 1, 2, 4 and 3, 6, 8, and so the centroid would be 1 plus 3 plus 2 plus 8, 1 plus 3 by 2. For the j dimension, we will be having 2 plus 6 by 2. I will be having 2 plus 6 by 2, and for the k dimension, 4 plus 6 by 4 plus 8 by 2. So the centroid belongs to the mean position of all the data points in the cluster. Now for each data point, we calculate the distance between the centroid and its data point using the Euclidean distance. So let me see a working example. And for this, it's a point A, B, C, D, E, F. We have feature 1 and feature 2. Let's assume it's an x and y, and we have the following, and I have the following data. So the step 1 in K means is to choose K, assuming K is 2 for now, for simplicity. And for the step 2, we'll randomly initialize the position of K centroids. K centroids means we have I have to create 2 clusters in my data set. So I'll start by randomly initializing the position of the 2 centroids, 1, 1 and 9, 8. That's random, completely random. Step 3 is assignment step. Assignment step is I have to assign each sample a label, a cluster. So the cluster, so I'll compute the distance of each sample with all the clusters and pick the nearest cluster as the assigned cluster. So here I am just computing the distance, and whichever is nearest cluster, I am assigning the data point to that cluster. Now the update step is when all the data points have been assigned some cluster, then I take all the data points, compute the mean of it, and update the centroid position. Then I'm repeating the step for all the centroids. Then I'm repeating the calculation of distances using update centroid position. I'm calculating the mean of all the points inside the cluster and updating the centroid position. If any data point changes its cluster, repeat again. Right. So I'll repeat the calculation of calculating the distance of each point to the centroid, and if the data point changes if any data point changes its cluster, I'll repeat the calculation again. This is how my algorithm converges. We can assume the algorithm is converged when the no point is changing the cluster, or centroid position is not changing drastically, or it's changing very negligibly, or else max iterations is reached. Now the final centroid position represents the center of the discovered clusters. It's similar to placing a magnet in the space of iron data points. So each magnet gets adjusted to the nearest iron data points. So it's So the k-means works similar to this only. So why k-means work? So k-means can be visualized as broken down. So k-means can be broken down into two steps. First is to assign each sample to the nearest centroid, and second step is the update the centroid position. So the main objective is to minimize WCSS. If any point inside cluster is as close as to the mean of it, variance is minimum, as every point is close to its mean value. So the variance is minimum, therefore WCSS is minimum. So clustering is simply just taking the two steps, assigning some centroid and updating the centroid, and we compute the quality of the cluster using WCSS. So how to choose the best value of k, which is an hyperparameter? We have a method called there is a method called elbow method. Using when I plot k versus WCSS, this elbow type structure is generally seen, where the WCSS stop decreasing significantly when we increase the number of clusters. So a sudden drop is seen right here. So the optimal cluster is 2. So this type of bent is generally the best value of k. What is the time complexity of k-means algorithm? Let us take n number of samples, k number of clusters, d number of features, and t number of iterations. For each iterations, to calculate the distance of n samples with d features and k clusters is O of n into d into k. And for updating the centroid position, it's n into d, which is an addition. So the final overall time complexity becomes n into d into k, and we do for t iteration, so n into d into k into t. The space complexity is also simple, for we have to just store the data points and the position of the k centroids. What are the pros and cons of k-means? Fast for large data sets. Even if the number of data points, even if the size of the data set increases, the k-means can work pretty well. Works well when clusters are roughly spherical or similar size. So a k-means has an assumption of that it works with the spherical shapes cluster only, because in n-dimensional space it assumes the data points are in spherical shape and of similar size. This limitation will be handled by another algorithms as well, but it's important to know that k-means has this assumption. It works roughly it creates clusters which are roughly spherical and have the similar size. So some of the applications are customer segmentation, market basket analysis, anomaly detection, document clustering, and medical patient grouping. What are the cons? Some of the limitations are: value of k should be chosen wisely and beforehand. So before starting the algorithm, even training the algorithm, I should know the value of k, which is very sensitive. So the algorithm is very sensitive to create the k clusters, and it is very sensitive to initial position of the centroid also. So if I randomly initialize a centroid, so the entire quality of k-means depends upon the initial position of centroid. and it is also sensitive to outliers, as the mean is also sensitive to outliers. So when my data set has lot of outliers, the formed cluster can be of bad quality. And lastly, performs poorly on non-spherical shape clusters or varying densities, as we already know that KNN makes this assumption. And it is sensitive to scale of the features, as Euclidean distances, as it computes Euclidean distance, and Euclidean distance is scale dependent. So this was all about k-means. Thank you.